Lots to talk about in this video, but I'm going to try to make it short and sweet so that you are prepared to do classwork. We are going to begin a formalized study of what it means in mathematics to prove that something is true. This is often done in geometry at the high school level because it's a great way for students to get a sense of what does it mean to formally prove something. That's why we've been studying a lot of reasoning. So take a problem like 44 minus 2 times 3x plus 4 equals negative 18x. So if you were going to solve this problem, I hope you would start by maybe distributing that negative 2. And then I think you may collect like terms and say 44 minus 8 is 36. And then you might add 6x to both sides and say that 36 equals negative 12x. And then you may divide both sides by negative 12 to say that negative 3 is equal to x. That is a formal argument, and when you make a formal argument, it is proper to justify your steps. Now, we have never made you do this, or we probably rarely made you do this, but we're going to do it in this unit so we can start to see the process. So over here, we started with this, and we call what we start with the given. Given that something is true. Then how did we get to this step? Well, we used the distributive property. And then how did we get to this step? Well, we collected like terms, or we added like terms. Now that's different than the next step where I actually added 6x to both sides. So we're going to call that the addition property of equality. And then we got here by dividing both sides by negative 12, so we're going to call that the division property of equality. And what we have here is a formal argument with our statements on the left and the justifications on the right. This is often a structure used in geometry called a two-column proof, where you have the statements and the logical accepted reasons for those statements. Good? Notice I used some properties that you've used before, but I gave them formal names. So we'll start this video by looking at formal names of lots of properties. Notice all of these properties are called algebraic properties of equality. The book abbreviates and says addition property, but I want you to say addition property of equality, subtraction property of equality. And they're the things that you've used in algebra. If you have a true statement, an equation, you can add the same thing to both sides. You can subtract the same thing from both sides. You can divide both sides by a non-zero number. You can multiply both sides by any number you like. The substitution property is really important. It says if you know two things are equal, then A can be substituted for B in any equation or expression, or vice versa. I'm going to call this the property. I'm going to call this the APE, addition property of equality, subtraction property of equality, multiplication property of equality, division property of equality. I will give you a lot of leeway when you use these if you use MPE or DPE, because those can be the same. What I would say is if you use MPE when you meant division, I'm going to give you full credit, because there is no such thing as dividing, there's only multiplying. Same thing with addition and subtraction. If you say APE because you add the opposite of a number, that's subtraction, but I would be fine with just that. So more properties that you might know, the distributive property. This is actually not even the formal name. It's technically the distributive property of multiplication over addition. I'm not going to write the whole thing out. You can just write, as I wrote in that example, dist prop. I'll know what you mean. You can abbreviate. But here are some properties that you may not know that are very important in our study of geometry. First is the reflexive property. The reflexive property of equality says for any number a equals a, ab equals ab if it's a segment, the measure of angle A equals the measure of angle A if it's the measure of an angle. And you might be thinking, when in the heck am I going to use this? Well, we use it a lot in geometry. A equals A. Here's an example. You might see it in something like this, where we talk about these two triangles being the same. A, B, C, D. If you know this is the same as that, and you know this is the same as this, why are these two triangles the same? Well, in a formal proof, you have to have a statement that says BC is congruent to itself. And that's a reflexive property. So this is something you need to notice. A reflexive property is literally saying a number equals itself. We can just write reflexive. Okay? Another property is the symmetric property. If you know A is equal to B, then you know B is equal to A. If you know AB is equal to CD, then CD is equal to AB. Again, another example where you might see this is when we prove triangles congruent. In this case, I have two triangles that if sorry, that should be a D. When I try to match them up, ABC looks like this, A, B, C. A has one mark, AC has two marks. Sorry, AB has one mark, AC has two marks, and I'll say BC has three. Well, if I draw the other triangle in the same orientation, D would be here, and it's DC that has one mark, DB that has two marks, and now CB that has three. Notice that this segment corresponds to CB, not BC to BC, but the letters are actually reversed. That's a form of the symmetric property, that BC equals CB. You flip those letters. It's not the same. So it's important that we have the symmetric property, that we can switch the order. Another important property is called the transitive property. If A is equal to B and B is equal to C, then we know A is equal to C. And what's really important when we use the transitive property is order. 1 to 2, 2 to 3, so then 1 to 3. You cannot use the transitive property to say 1 to 2, how do I want to say this? Sorry. 3 to 2, then to say 1 equals 3 is substitution, because you're substituting 3 in for 2. And I know you're saying, wait, Stubbs, there's a lot of information coming. This is such semantics. Well, welcome to math. Math is a lot about precision of language. And when you make an argument that goes 1 to 2, 2 to 3, then 1 to 3, that's transitive. And when you make an argument that goes 1 to 2, 3 to 2, so 1 to 3, that's substitution. And guess what? You're going to lose points if you don't know the difference and you can't tell. So something to practice here is paying attention to those properties. Take a look at this example. We're given that LM is congruent to PN and that XM is congruent to XN. And it should be pretty obvious in our heads that this would be the same as this. But right now, let's take a look at the formal argument on how we would show this. These statements are our givens. They were given to us to be true, so we're starting with our givens. Now I'm going to say that LM is equal to PN and XM is equal to XN. Well, if you look in your definition dictionary, you would see that this is the definition of congruent segments. It says two segments are congruent if and only if their measures are equal. So why can I go from congruent segments to equal measures? Definition of congruent segments. LM equals LX plus XM. What says that one big segment is the sum of these two smaller segments? That's the segment addition postulate. We actually can't prove that. We just assume that to be true. Now here's the tricky one. LM equals this, PN equals this. I'm now going to say that LX plus XM equals PX plus XN. That's actually taking this and substituting it in here, taking this and substituting in there. So this is the substitution property, and we did that property twice. Now I'm going to say that LX plus XN equals PX plus XN. Notice I'm now substituting XN for XN, so that's the substitution property again. But I can't do that in one giant step. I have to go one step at a time. The next thing I'm going to do is I'm going to say XN equals XN. Why does something equal itself? That's reflexive. And you might be saying, you don't need to say that. And it's like, well, I haven't said it yet, so I do. And now how would I get to this statement? Oh, I took this one here and I subtracted xn from both sides, so that's the subtraction property of equality. Now I have equal measures. I can say the segments are congruent using definition of congruent segments. So the reason I've been asking you to keep all of those definitions in your dictionary is because those are the reasons that go here. If you haven't been keeping up with all of those things, you're kind of behind the 8 ball, and you got to start doing that. You've got a lot of definitions to go through. I will give you a list for you to work off this weekend to make sure you have all the definitions. But you can start to see this is what it takes to prove without a shadow of a doubt that this is the same as that. Even though we could kind of know that right away by looking at it, this is the formal proof. You actually have to slow your brain down and try to just do one step at a time.